Hello students, welcome back. Previously, we established the modular arithmetic. Oh, excuse me, wrong section. Previously, we established the modular arithmetic. Basically, we can add and multiply freely as long as we have the same modulus. And we went through the first example here, modulo 9. Let's repeat that as an exercise. So 3 to the 5th power. 3 squared is 9, and that's 0. So 3 to the 5th power is 3 to the 2nd power times something. 0 times something, so this entire thing is 0. How about 4 to the 7th power? That's trickier. 4 squared is 16, which is 18 minus 2, so it's negative 2. Yes, you can use 7, but negative 2 is simpler because we have smaller number parts, smaller absolute value. And then if I square it again, then negative 2 squared, so we have 4 again. So 4 to the 4th power is back to 4. Does it help? Oh yes, 4 to the 7th power can be rewritten as 4th power times 3rd power. But 4th power is back to 4. Back to 1st power, 1 plus 3, back to the 4th power, which is back to 4. So we have 0 and then 4. Finally, how about 7 to the 8th power? 7 is actually negative 2. 7 is congruent to negative 2 modulo 9. And that's easier because the number part is smaller. So 7 squared and negative 2 squared, so that's 4. Okay, squared gives me 4. So 8th power is 7 squared to the 4th power. 4 to the 4th power, going back to 4. So what do you have? 0, 4, 4. Yeah? 0 times 4, 0 minus 4 times 4, so negative 16. But 16 is congruent to negative 2, so this is negative of negative 2, back to 2. Well, we can do direct computation with Mathematica. Just calculate this thing, 3 to the 5th power minus 4 to the 7th power times 7 to the 8th power, and divide by 9 and take the remainder. And yes, indeed we have 2. But of course, if you don't have technology aid and doing this kind of computation with traditional paper and pencil, good luck about that. How about the next problem? Same expression, but this time modulo 6. Okay, let's consider same thing. 3 to the 5th power. 3 squared is 9. So 3 squared is 9. So that's congruent to back to 3 modulo 6. So 3 to the 5th power is 3 to the 4th power times 3, and that's 2nd power squared. So that's 3 squared is back to 3, so that's 3 squared times 3, and 3 squared is back to 3, so that's 3 times 3, so 3 squared back to 3. Is that what you're getting? Yeah, back to 3. So this thing here, blue, green, and then purple. This can be rewritten as okay, this is 3. Okay, how about 4 to the 4 to the 7th power? Um, 4 squared first. That's, no, 4 is congruent to negative 2. That's going to be more convenient because we are doing modulo 6. we can reduce the absolute value. So 4 squared is congruent to negative 2 squared, that's 4. So 4 squared is back to 4. All right. 4 to the 7th power can be written as 4 squared to the 3rd power. That's going to be up to 6. No. Let's do it this way. 4 squared, another 4 squared times 4. All right. 2, 2, 2, 6, and then 1. All right. And then observe that they're all 4s. 4, and then 4, and then 4, and then 4. Wait a minute, why am I doing it like this? Let me write everything as just 4 to the 4th power. So 4 squared, and then squared is back to 4. So back to 4. Is this really the best way? Probably not, but wait a minute, here I stopped short. Is this the best way? Anyway, there may be probably a better way, but anyway, it's 4. Okay, all right, you got that. And then 7 to the 8th power. Let's see. 7 is congruent to 1 modulo 6. So 7 to the 8th power is congruent to 1 to the 8th power. Oh, that's 1. So this is 1. Yeah, that's 1. So we have 3 minus 4, which is negative 1, which is 5 modulo 6. Well, here's a verification. Yes, we have 5. Okay, we can do these kind of modular arithmetic. Tedious, but we can do those. Here's a little bit clever problem. 1 factorial plus 2 factorial plus 3 factorial plus and so on up to 100 factorial modulo 12. And you gotta be crazy to attempt this kind of computation first. So 1 factorial is, 1 factorial is 1. No question about that. Oops. 2 factorial is 2 times 1, so 2. 3 factorial is 3 times 2 times 1, that's 6. 4 factorial is 4 times 3 times, so this is 24. And that's congruent to 0. All right. And then 5 factorial is 5 times 4 factorial. So 5, and then 4, 3, 2, 1. And that's 0. And so on and so forth. So basically what you get is everything is 0 except for the first 3 terms. So we are going to get 1 plus 2 plus 6, which is 9 modulo 12. Looks like that's what I'm getting. Let's try. And then n is greater than or equal to 0, then all factorial will be 0, yes. So, yes. By the way, I'm curious, will Mathematica handle this? Oh no, excuse me, it wouldn't handle dot dot dot, so I have to use sum and then k factorial. K is running from 1 to 100. Well, it did handle very quickly. So apparently it did not do this summation and factorial computation. It must have done it in far more clever fashion. Okay, how about the next problem? If the 15th of June is Thursday, what day is the November the 15th? Well, we're dealing with days of the week, so this is mod 7 operation. So June to July, how many days are there? June 15th to July 15th. June has 30 days, right? And then July has 31, August has 31, and September has 30, October has 31, and that's it, isn't it? Yeah, June, July, August, September, October, and then November. Okay. And then you have to do mod 7 operation. But then again, please recall that 28 is congruent to 0. So this is 2 plus 3 plus 3 plus 2 plus 3. So 2 plus 3 is 5, 5, 10, 13, which is congruent to 81 modulo 7. So Thursday, then minus 1. It should be Wednesday. Yeah, it should be Wednesday. I'm pretty sure I did it right. Let's see, what's my solution here? Yes, Wednesday. Enough time for another example problem, fast modular exponent. Okay, all right. We're going to talk about the next example in a separate video, but just one comment. Yeah, in this problem, we applied mod 9 operation to the base. We can do that because we are repeatedly multiplying the base. 7 is being repeatedly multiplied on and on and on. You cannot apply the modular operation, modular arithmetic, to the exponents. It is just counting. So if you do mod 41 in this case, you can do that to 2, and how much will that helpful? Something to think about. And then mod 645, yeah, but you cannot apply that to the exponent. So this thing is not equivalent to 2 to the negative first power. You see? 2 to the 644 is not congruent to 2 to the negative first power modulo 645. You cannot apply that to the power. How do you do it then? Well, that's something we are going to discuss in the next video. For now, let's be content with the first example problem.